We now consider a hypothesis testing problem that involves a proportion. This problem comes in three parts. A die is rolled 150 times, and it comes up heads 37, comes up 37 times. Is this evidence enough to think that the die is not fairly balanced? Use the significance level of 0.05. Then we have questions about the power of the test that follow. To begin, we note that this is a hypothesis testing problem, and the question involves the proportion p that the coin, or the die, lands 6. The null hypothesis would be that the die is indeed a fair die, and that p is equal to 1/6, while the alternative hypothesis would be that the die is somehow unbalanced. Now, in this problem, there's nothing specifically saying which way the die is balanced. There's no a priori knowledge before rolling it 150 times whether or not it should come up 6 too many times or too few times. And so we will be conservative and use a two-tailed test for this particular problem. Just a reminder that a two-tailed test should be used if there's no a priori reason to think that the chain should go one way or the other. A one-tailed test should be used if you have a good reason to think before doing the testing that the difference should be an increase or a decrease. But simply rolling the die 150 times and observing that it lands heads or lands 637 times is not a good reason by itself to conclude that p should be greater than 1/6. If we had some a priori reason to think that the die was unbalanced to land 6 too many times, then that would be a reason to use p is greater than 1/6. Okay, so we have our null hypothesis and alternative hypothesis. Okay, now this is going to involve the normal distribution, and so we have that the test statistic z is equal to the observed proportion minus the expected proportion divided by the standard error for the proportion under the null hypothesis, and the proportion that I need will be for the standard error will be the proportion under the null hypothesis. So for this problem, the observed proportion is 37 over 150. The expected proportion will be 1/6, and then I divide by the standard error for the proportion, which will be 1/6 times 5/6, divided by the number of trials, which is 150. Okay, so we do the arithmetic, giving us a z statistic of 2.62907. For this, we will use the bell curve. We don't have a standard deviations that we're approximating, so we just simply will use the bell curve using the central limit theorem. So we have a bell curve, and this time we have a two-tailed test. So I need the total area that's being shaded here to be equal to 5%. So that leaves 0.025 on the left tail and 0.025 on the right tail. And as always, if we have a value that's out to the far right or to the far left, the decision will be to reject the null hypothesis. Either to the left or to the right. While in between, the decision will be to retain the null hypothesis. Okay, so to make this determination, we need to figure out the cutoff value. The cutoff value, z critical, will be z of 0.025. So that 2.5% of the area lies to the right of the mark. So we find that with Excel or using a calculator. So norm S inv of 0.975 gives us 1.95996. Okay, so we see that the mark 2.62 will lie in the rejection region. And so let me clear this out so I can type our conclusion. And our conclusion is that we reject the null hypothesis. It appears that the die is unbalanced. So that is the conclusion we make for the first part of this exercise. Let's now turn to the consideration of power. And to do that, let me clear off our conclusion here and make a little bit more space. So to look at the first power question, we suppose that the true chance of landing 6 is 0.2. How likely is it that a level 0.05 test based on 150 rolls will not detect such a departure from the null hypothesis? So that is the probability of making a type 2 error, that we retain the null hypothesis, we do not detect such a large departure, even though the alternative hypothesis is true. To do this exercise, we have a formula that can be derived in a fairly similar fashion to what we've seen before, and the formula is here. So this is the formula for the computation of beta, and this has a somewhat similar form to the formulas for beta that we had involving formulas for an average, except this one is a formula for a proportion. So we have the standard error for proportion in the bottom where we had sigma before. So this is where we have, this is our formula for beta for our proportion, and now we just simply have to compute this thing. For this problem, we have that P naught under the null hypothesis was 1/6. The hypothesized correct proportion under the alternative hypothesis is 1/5. And we also have that n is equal to 150. We also worked out what z alpha was, which is 1.95996. So we have all the information that we need. Now it's just a matter of simply typing all this into a calculator or Microsoft Excel and being very careful with the calculations to make sure that what's plugged in is actually correct. Okay, so let's go ahead and start typing. First, the first part will be equal to, let's see, the numerator is going to be 1/6 minus 1/5 plus z alpha, which was 1.95. Well, let me do it like this. First, let me put norm s in 0.975. That is our z alpha. And then the first argument, stretch this out nice and big, is equal to 1/6 minus 1/5 plus the z alpha we just got times the square root of 1/6 times 5/6 times 1 over n. So that's the numerator divided by the square root of 1/5 times 4/5 times 1 over 150. So that is the argument for the first part. The argument for the second part is going to look very similar, except, and let me put a star on this so I can actually just simply copy and paste the thing. So if I copy and paste, I get the same number I had before. The difference is that I have a minus sign in front of the z instead of a plus. So this is going to look very much the same as what I typed before, except I have a minus here as opposed to a plus. So negative 2.846. So norm s dist of the first number is 0.7897. Do the same thing for the second number. And then the difference between them is going to be the beta. So beta will be equal to the difference of these two things, and so our beta is going to be 0.875. So we'll go ahead and write that down. So that 0.875 so 0.7875, and that is the computation of beta for this problem. That's a fairly large value of beta. we now finish this with the third part of the problem. What should the sample size be to ensure that beta of 0.25 is equal to 0.01? So before we had, if p prime was equal to 0.2, we had a beta that was certainly not that small. How big should the sample size be so that beta of 0.25 is equal to 0.01? To do this, we have the formula that was discussed in class, which you now see on the screen. This formula parallels the formula that we had in the past for the computation of the number of, or the size of the sample required for a given power for a sample mean. For this problem, we have z of alpha for 2, which we found before, 1.95996. We also need z of beta, for beta is equal to 0.01, and p naught p prime. So the information we need is in the problem. So our z of alpha for 2 is already given. Z of beta we'll figure out, where beta is equal to 0.01. Our p naught is equal to 1/6. And our p prime is equal to the new hypothesized proportion, which is 1/4. So now it's a matter of plugging into a calculator or Excel and being careful not to make a mistake. Okay, so I'll use Excel to do this. To get started, norm s in 0.975, that is our z alpha, and our z beta is going to be norm s in of 0.99, so that 1% of the area lies to the right. And so finally our answer is going to be a 1 z alpha times the square root of 1/6 times 5/6 plus z beta times the square root of 1/4 times 3/4 divided by p naught minus p prime, and then this whole thing has to be squared. And so I believe I typed it in right, and so it looks like I need 435 rolls in order to be able to ensure that the beta is equal to 0.01, or a power of 99%. So the answer is 435, just simply plugging in to Excel or a calculator and being careful not to make a mistake.